So if you need to watch this video, it would be about reviewing rationalizing of square roots. Now, it may or may not be something that you might have had before. So there's also a help sheet available called Basic Square Root Functions. That number 1, 2, and 3 on the first page of that are things I'm going to be expecting that you should be able to do. So this video is reviewing some of those and me talking through them so that you can see what's going on to rationalizing square roots. Because if you just use a calculator, you'll get a decimal value most of the time, and the decimal value is not accurate or helpful when you're dealing with many of the problems that we're going to have in class. So you can see it says I can rationalize square roots, which means there's no perfect square under a radicand, the square root symbol, and there's no square roots and there's square roots in the denominator. So you can't have square roots in the denominators either. So here are the type of questions that we're going to have. So for instance, you'd have the square root of 18. And that is not simplified because there's a perfect square underneath that 18. Remember, perfect squares are things like 4, 9, 16, 25, and so forth. Numbers that are perfect squares, like 2 times 2 or 3 times 3 or 4 times 4. So one way of looking at this is to say, well, the square root of 18 has a 9 in it. The square root of 9 is a perfect square. 9 times 2 is 18, and therefore the square root of 9 is 3. So you have a 3 on the outside and a 2 left on the inside under the square root. So the answer is 3 square root of 2. Some people prefer to do it like this. They'll break down the 18 into all its component parts and say, oh, that's 2 times 3 times 3, like a prime factoring. And they look for double roots, say, oh, there's a square root of 3 times square root of 3. Well, square root of 3 times square root of 3 is 3. So you could also do it like that. So however you do it, you need to have a 3 on the outside, not under the square root because that's something's being done to it, and the 2 is in the inside because it's still under the square root. Now, what would happen if we had a 5 on the outside? That means 5 times that thing. So since we just did that problem, that would be 5 times 3 square root of 2, which means it's 15 square root of 2 now. All right, so what about a square root that's in the denominator, like this one? So in this one, we have a square root in the denominator, and that violates the rule. Now, this came from a time when people didn't know how to divide by irrational numbers like the square root of 5, so they figured out a way of multiplying by them. So it worked out better. But at the time, people couldn't do it. So to be able to do this now, so that we all get the same answer, the trick that we use is that we're going to multiply the top and bottom by the square root of 5, because that's like multiplying by 1. Anything over itself is the same as multiplying by 1. It just changes the form. Like the same reason why we can divide fractions, because we're dividing the same thing from the top and bottom. Well, the bottom is square root of 5 times square root of 5, which is 5. Now it's no longer got a square root. And the numerator is 3 square root of 5. So I know that it's probably not simpler, but it is rationalized. So rationalized because it's got no square roots in the denominator, and it's got no perfect squares underneath the square root symbol. So we get something like this. It's a little messier, but it's got the same problems. Now, what I would like to say is, anytime we can simplify numerator and denominator, we should do it. So for instance, if you thought about the square root of 14 over 6 as the square root of 14 over 6 with all under the same radical, we should be able to reduce that thing. So I'm going to reduce the 25 over 10 because they both have a 5 in them, right? 5 goes into 25, 5 goes into 10. And the square root of 14 over the square root of 6, they both have a 2 in them. So I could reduce that to 7 over 3. So it's not finished and it's not better, but it's easier. So I've got a 3 in the denominator that's under a square root, so I've got to get rid of that by using our little trick, multiplying the top and bottom by the square root of 3. So what I've got in the bottom is 2 times the square root of 3 times the square root of 3. Remember, the square root of 3 times the square root of 3 is 3 because it's like the square root of 9. So we don't have to say it's 9. Just like if I had the square root of 17,458 times the square root of 17,458, it would be 17,458. So we got 2 times square root of 3 times square root of 3, which is the same as 2 times 3, which is 6. And the numerator, since those square root of 7 and square root of 7 and 3 are both under a radical, we can multiply them together. Now, 5 and 6 have nothing in common, and 21 has no perfect squares in it. So that's the simplified version. The problem here is if you had multiplied by the square root of 6 and the square root of 6, you would have ended up having to reduce a lot in the end. So by doing this, sometimes we can avoid having to simplify later. It's always easier to simplify first. Like, for instance, the square root of 12 in the denominator here, instead of just multiplying the square root of 12 over the square root of 12, which will work, but will take longer, I would rather take this 12 and break it down because there's a 4 in it. See, it's 4 times 3, right? So that's the same as 2 square root of 3 in the denominator because it's square root of 4 times square root of 3. And the numerator is 3 square root of 5. Nothing's changing there. Now I can multiply by the square root of 3 over the square root of 3. And in the denominator, it gets the same thing as before. 2 times 3 is 6. Didn't mean to do that. And the numerator is 3 times square root of 5 times square root of 3, which is 3 square root of 15. Now this one has something that I can still do. Now the square root of 15 and the square root of 6 both have a 3 in them, but that's not what's important here because the square root of 15 is under a radical, and it's not going to divide with something that doesn't have a radical. So what we're going to be able to do here is take the outside numbers and divide those. 3 over 6 is the same as 1/2. So our answer is square root of 15 over 2, which is slightly simpler than the first one. Okay, and this other one, let's see if I have anything below here. No, the other one, the last one here on this page is 6 square root of 50. 50 breaks down, it's got a perfect square in it of 25. 25 times 2 is 50. Square root of 25 is 5, so that's like 6 times 5 times the square root of 2. So the answer is 30 square root of 2. All right, that's how we simplify radicals, the most common types. So you could try these if you want. If you want to pause and check these out, go ahead and pause now. All right, let's see what you got. So negative 6 times the square root of 4 times the square root of 2. Negative 6 times 2, because 4 times 2 is 8, and 4 is a perfect square. 4 is on the list, right? So I can simplify to this thing here. And this one, the answer is the square root of 14 over 7. I got one more type of problem that's a little bit different. And this one, we rationalize in a different way. I don't think this is on the sheet, and I'll probably have to do another video on it. But this is called rationalizing when you have something that's not so easy in the denominator. The problem here is if I just multiply by the square root of 7, it's not going to work because this is like the square root of 7 times 3. Well, that'd be 3 square root of 7 plus 7, and that really doesn't help. I've still got the square root in the denominator. So what do you do in this case is you multiply by the only thing that's going to get rid of the radical in the denominator, and it's called the conjugate. The conjugate of 3 plus square root of 7 is 3 minus the square root of 7. So I'm going to multiply by 3 minus the square root of 7 on the top and bottom, because if you multiply out 3 plus 7, 3 plus square root of 7, and 3 minus the square root of 7, it's kind of like a difference of squares type problem. You're going to end up with nothing in the middle. So 3 times 3 is 9, and then we have negative 3 square root of 7. And over here is positive 3 square root of 7. And negative square root of 7 times negative square root of 7 is negative 7. See how these are going to add up to 0 because they're conjugates, which means the inner and outer term is going to add up to 0. So what we end up with is just 9 minus 7 in the denominator. That's because that's all that's left. In the numerator, we can take 4 times 3 and 4 times square root of 7. We get this answer. Now, we could actually simplify that just a little tiny bit more. Wish I'd put that somewhere else. And because we have 12 over 2 and 4 over 2, we could actually divide out of 2, which would make it even simpler. I'm going to put it to the left, even though because I've run out of space, but I'm going to say 2 goes into both of those, so it'd be 6 minus 2 radical 7. That's our final answer, because 2 goes into 12 and 2 goes into 4. We could split that up into 12 over 2 minus 4 radical 7 over 2, or we could just do 2 into both of them. All right, so this is about rationalizing square roots, and I'm sure there'll be more to be said about this.